Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to introduce ourselves to the product rule for differentiation. Now, the product rule for differentiation is the rule that I've been warning you about in previous videos, specifically the videos on derivatives of polynomials and exponential functions. I had stated at that time that the derivative with respect to x of a product of two functions is not equal to the derivative of the product of their derivatives. It's totally not equal to that. We do have a rule that says if that was instead a summation, then it is true that you can break this apart into a summation, but not if it's a product. Products are very much more complex in differentiation and in actually calculus in general. So what is the product rule? Well, if you're given a couple functions that are both differentiable, that's key here, they both have to have derivatives that exist, then the derivative of their product is not equal to the product of their derivatives. Instead, it's the derivative of the first function times the second, so the second function you're not taking the derivative of, plus the first function times the derivative of the second. So again, the derivative of a product is the derivative of the first function times the second, plus the first function times the derivative of the second. Each function you're eventually going to take the derivative of, it's just that you're going to multiply them against the other function's non-derivative, I guess you could say. Zeroth derivative is what we normally call it. That is Leibniz notation. However, if you want Lagrange notation, it works like this. The derivative of a product, so the derivative of f times g, is f prime g plus fg prime. That's actually what I think most of us prefer to remember it as, just because it's simpler as far as notation. So we're going to go ahead and jump into a proof of this before using it. Now, this proof is really very interesting. It's also one that I would not imagine a student can make up at the last second or even memorize their way through, but it's a really good proof to see. So we want to investigate the derivative of f times g. So let's go ahead and start with that. The derivative with respect to x of f times g. It's really f of x times g of x, but we'll just write it like that. Well, by definition, that's the limit as h goes to 0 of the difference quotient. Instead of f of x plus h minus f of x, we have a different function name here. It's f times g at x plus h minus f times g at x, and that's all over h. And that so far should be okay. Right? I'm just not using the same function name as I was in previous derivative examples, limit derivative examples. Instead, I'm using a different function name, fg. It doesn't really matter. It's the same thing. Now, for purposes of this proof, it really works nicely to see a visual. And this happens actually if you read any textbook in calculus, they usually have this visual, and it's a beautiful visual. So let me give you a wonderful look at the world of geometry and calculus put together. So let's suppose that this side length from here to here is the value of f at x, whatever that may be. So I'll just say f at x. And the other value, I'll use green for that, this guy right here, we'll call the value of g evaluated at x. Therefore, it should be somewhat obvious that the area of that square is just the product of f and g evaluated at x. Now it's critical to remember these lengths, vertical length and horizontal lengths, represent the outputs of our function. It's going to be critical to understand this proof. So what if we were to be able to change the output of our function for f just a little bit? In other words, we wiggle the output of f ever so slightly. So we say we have I need a better looking delta there. We have a delta f here. We wiggled the output of f. Well, that output wiggle is the result of us wiggling the input for f. So I'm going to argue here that that change in output for f is really a result of starting with, actually maybe just to say this, it's the result of starting with f of x, but having adjusted that x value slightly. So I'm going to write it like this, f of x plus h minus f of x. Now, I do want to mention here that my notation is a little bit sloppy, mainly because normally when you're arguing like this, and you'll see this in a textbook, they don't use h, they'll use delta x there. The reason why they use a delta x is because technically h is used within the limit. H is tending to 0. But honestly, for our argument, I'm totally okay with just saying, like, let's look at f of x plus h minus f of x. Now, if you think about that, that's like a y2 minus a y1. That is totally a change in y values right there. So it is actually a change in y values. Remember, y is just the function. So this is why when I said I'm going to argue that this delta f is just this difference, it's easy to argue that because that is y2 minus y1, which is totally a difference or a change in f. I'm going to do the same thing for g. Down here, I'm just going to say, what if we were to wiggle this green length a little bit? And that green length is an output. So what if we were to wiggle the output of g a little bit? And again, I will just say that's the same as g of x plus h minus g at x. Again, it's just a y value minus a different y value, which is a change in y values, which is what that is. So there's no real craziness to this argument, at least yet. Now, before we had this vertical length f and this horizontal length g, and we said, oh, the area of that square is f times g evaluated at x. We can also find the areas of these rectangles right here, this one and this one, using a similar argument. This rectangle right here, I'll just do that. That rectangle has a height of delta f and a width of g of x. So I'm going to go ahead and write that in there. This has a height, a delta f, and a width of g of x. Along the same lines, the height of this rectangle is f of x, and its width is delta g. So again, the area will be height, f of x, times width, which is delta g. Finally, you can easily see that small little box right here. We can find its area, its area by height times width. The height is delta f, the width is delta g. So delta f times delta g. I hope that's okay. That's just, these deltas just mean slight changes in output. That's all I'm really saying is I have a slight change in output. Nothing big. Now let's zoom out because I need to bring this back to my proof. And I need to somehow relate this to my limit within my proof. Well, if we've defined the change in f to be f of x plus h minus f of x, and likewise defined the change in g to be g of x plus h minus g of x, then fg of x plus h minus fg of x, that picture must be, by our definition, a change in f times g. Just by our definition. It's the same exact definition. So if you consider that to be true, and it is actually true, that's our change in output for f and g, for the product of f and g, then let's look at our picture here. Well, f times g is just this area here. But when we wiggle the inputs, there's a change in the area that I'm highlighting. That change is going to be the second area that I'll highlight here. All of this extra bit is actually the change in the product. Originally, the product is that yellow area, and then we changed the inputs slightly. We just wiggled them a little bit to grow this. And so G slightly grew, F slightly grew, and their product grew to include that blue area. This gives us some way to relate out that numerator for something a little bit different. So I'm going to hop over here and say thus, and I'll write right here, the change in f times g is the same thing as f times g of x plus h minus f times g of x. That was just using our argument from before. And by the way, I should note, normally people would put parentheses around a product of functions there. Sorry about that. I'll do that down there too. Okay, so all I'm saying out loud now, or writing down, is what I said out loud earlier. The change in the delta in fg is just that numerator. Just like the delta in f is likewise the numerator of the difference quotient. And the change in g, again delta g, is the numerator of the difference quotient. So is the change of fg. It's the numerator of that difference quotient. However, we can also see the change in fg is that blue area. Let me write that down. I'm going to zoom in so that I can write it down cleanly. So, however, geometrically, the change in fg, the wiggle, is all that blue area. So it's going to be the change in f times g of x plus f of x times the change in g of x plus the change in f times the change in g. Again, that's just all that blue area. And hence, we can trade out that numerator in our difference quotient for the derivative, which is fg of x plus h minus fg of x, for delta f times g of x plus f of x times delta g plus delta f delta g. So that's what we're going to do here. We're going to just go ahead and rewrite this numerator in our limit up here with those changes. Now this is going to be a slight substitution nightmare, not major, but just a minor one. So this is a limit as h goes to 0 of a big old fraction. It was a delta f, technically of x, times g of x, plus a f of x times delta g, technically of x, plus delta f of x times delta g, again, of x, all over h. I just substituted that in from down below. Now remember what delta f and delta g stand for. They're the numerators of their difference quotients. F of x plus h minus f of x, and g of x plus h minus g of x. Let's insert those into this argument. This is equal to the limit as h goes to 0. Delta f is going to turn into f of x plus h minus f of x, by our definition, times g of x, plus f of x times delta g, again, was g of x plus h minus g of x. And finally, those delta f's and delta g's. Well, delta f was f of x plus h minus f of x. And delta g was g of x plus h. You can see there's a long numerator minus g of x. I almost ran into my figure off to the right-hand side. And that's all over h. Well, you know what? Rather than writing it all over h, I'm going to write it as three separate fractions. This over h, this over h, and this last one over h. And we know that we can split, actually maybe I should even say that's all within the same limit, so it's not an illusion here. We know we can split a limit as long as each of the splits exist. That's a limit law. So let's go ahead and do that. I got to move my text off to the right-hand side here just to give myself a little more room. So let's go ahead and split this limit. This is going to equal the limit as h tends to 0 of f of x plus h minus f of x all over h. And by the way, that g of x, I'll highlight it, does not rely upon h. So I'm going to factor it outside of that limit if you don't mind. Plus, now the second term here. Again, f of x, I'll highlight it, does not rely upon h. So I'll factor it out of that specific limit, and I'll have the limit as h goes to 0 of g of x plus h minus g of x all over h. So far, argument-wise, this should be agreeable to everybody. Everybody should be on board with this. The last one, everything does rely upon h. So I'm going to go ahead and say this is plus the limit as h goes to 0 of these fractions. What I'm going to do is actually split it into two different fractions. I'm going to split it into, maybe I'll do this. I'll do f of x plus h minus f of x times the limit as h goes to 0 of g of x plus h minus g of x. And this one I'll have over h. So I just split this fraction into two different fractions, one being f of x plus h minus f of x over 1, and the other one being g of x plus h minus g of x over h. If you multiply them back together, you get the same thing, so don't worry about it, don't freak out. Now, this might be illegal. So breaking these limits apart like this, it could be bad news. We just have to see if these limits exist. If they do exist, then we're okay. The assumption right from the beginning of the theorem is if f and g are both differentiable. Well, if they're both differentiable, then their derivatives exist. And you could see that this picture right here is f prime of x. And since they told me that exists, I will write this as g of x times f prime of x. And they also told me that g was differentiable. So this picture right here is also just going to turn into a beautiful g prime of x. Now, you can easily see since g is differentiable, this must be g prime, right? So I'm going to say plus something times g prime of x. And the big mystery is, what is this limit right here? As h tends to 0, what does f of x plus h minus f of x tend to? And this just requires us to remember that if you have a function whose derivative exists at x, then it's continuous at x. And if it's continuous at x, then as that h approaches 0, this will approach f of x. And thus, you will get f of x minus f of x, which is identically 0, and you will have 0 times g prime on the end. Again, I want to say that again because that's critically important. Because we're told these derivatives exist, f and g are differentiable, they must be continuous. Differentiability implies continuity. It doesn't work the other way, by the way. Continuity does not imply differentiability. So, the fact that this function f is continuous If I wanted to, I'll show it as an aside so that everybody's kind of on board with this. I could say, as an aside, I have this limit as h goes to 0 of f of x plus h minus f of x. And somebody says, hey, you know what? One of those doesn't even rely upon h. I go, oh yeah, you're right. Okay, let me write it this way. Limit as h approaches 0 of f of x plus h. And then this minus f of x, that's just a constant in terms of h. H is not moving in there, so I've moved that outside the limit. So this is what I'm taking the limit of. But because you told me f was differentiable, then f must be continuous. So as h goes to 0 here, this limit will be f of x. And that, you're still subtracting f of x off the back end, that will be 0. Yay! So that's why I got that 0. Now notice the end result here. The end result, if you allow me to rewrite it in a different order and using Leibniz notation, I'll write f prime in front, so derivative with respect to x of f, of x technically, but I'll just leave it like that, times g of x, plus f times the derivative with respect to x of g, plus 0. What have we shown? That the derivative of the product of f and g is equal to the derivative of f times g plus f times the derivative of g, which is the product rule. And we are done. QED. That's a really nice proof. I'm not saying that it's really nice that I've done it. Somebody else did it, and I've studied it. But it's a really nice geometric proof. It kind of glues together geometry and calculus simultaneously. It's a beautiful idea. So I highly recommend that you study that. It's a really, really nice one to truly understand how proofs kind of work and in different ways that you can use mathematics within a proof.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.